Okay. Okay. All right. Should we start or should we wait a little?
Yeah, let me introduce our
Okay.
speaker. Aditi is a fifth-year PhD student advised by Danksharding at Stanford University. And today she will give the talk about data availability sampling with repair.
Perfect. Yeah. Thank you, Naja, for the introduction. That's very sweet. Okay. Yeah. So I guess I can get started. So just to mention, this work is joint with my advisor Dan Pune along with Joachim Noy and Valeria Nikolenko, who are researchers at A16Z Crypto. But first, I just want to briefly talk about something a little different, which is threshold cryptography. So just at a high level, threshold cryptography allows you to reduce trust in any single party by splitting your secret value. So you may imagine you have some secret S, which could be a secret or some signing key or decryption key. And what you can do in threshold crypto is split the secret among many parties, let's say with the out of n secret sharing. And then sort of the guarantee that threshold cryptography gives you is that a quorum of any T shares is enough for the cryptographic task. So for example, if it's encryption key, then any T parties can decrypt the ciphertext. And the security guarantee says that no one can do the cryptographic task if they collude with less than T parties. So that's sort of the security property that threshold crypto gives you. But the key issue that was sort of overlooked in threshold crypto was this notion of accountability. So at a very high level, the question we ask is how do we deter parties from selling their secret shares in this crypto system? So in any of these scenarios, let's say threshold decryption, secret sharing, or threshold VRF, the question is what if some parties in a committee are selling their secret key shares? So pictorially, imagine that in threshold decryption, an adversary offers to pay $100 to, let's say, two parties in your committee in exchange for their shares. So like perhaps like these parties will agree to like sell the shares for $100, and now the adversary has two key shares. So for example, if the threshold was 2, now the adversary can decrypt any ciphertext because it has enough key shares. What we want in the notion of accountability is to be able to trace this sort of thing to back to the parties which are doing this. So in this example, let's imagine that the parties sold this box with this green sort of like border, which has the secret keys of those parties in it. So this box could be like anything that these parties make. For example, they could use obfuscation to make this box, they could use a TE, anything that they do to sell some information to the adversary. What we would like is if a whistleblower comes and tells us that this information was sold to me, then we should have a tracer party which can look at this information and say that parties 1 and 2 were the ones who sold their shares and made this green box. So this is sort of like a very high level picture of accountability. If some parties are selling their shares, we want to be able to trace that information back to those parties. Any questions on this motivation? So this notion of accountability has been explored in the recent few years, starting from accountable threshold signatures, which were formally defined in 2001, but there's been some recent works in getting stronger security properties. And I guess a few other directions are accountability in threshold decryption. This was formally defined in 2024, and there's been a lot of recent works on getting, again, stronger security properties. And then we have accountability in secret sharing, started from 2021, and again, more works in stronger properties and like going beyond threshold and so on. And lastly, we also have accountable threshold VRFs. And oh yeah, I will be presenting 2 of these papers at Eurocrypt, so hopefully I'll see you there. And yeah, just lastly, there's like lots of open questions in this space, and I'd be happy to talk about this after the talk. So now let's come to data availability sampling, which is the main topic of today. Okay, so I'll start motivation with a consensus, which is sort of the building block of pretty much all blockchains today. So just at a high level, the way consensus works is we have a bunch of validators, which are the computers here. They look at a pool of transactions coming in from the network, so that's the files on the left. And then they run the consensus protocols and they output an ordering on these transactions. So like it's like blue and green and then red. And then the execution engine of the blockchain will take this ordering and execute these transactions, meaning it will update the state of the blockchain based on these transactions. But the problem is as there's more and more transactions coming in from the network, this consensus layer quickly becomes a bottleneck because consensus has at least sporadic overhead in terms of compute and communication. So this is sort of the key problem we're dealing with today. And one solution that has been proposed to scale consensus is something that we call decoupling the ordering of transactions from their dissemination. So let me show you pictorially what this means. So again, we have a bunch of validators in the middle, and we have a pool of transactions coming in from the left. But now what we'll do is, instead of asking every validator to look at every transaction, what we'll do instead is we'll have these paper clips, which are the references to these transactions. So like the green paper clip is a reference to the green transaction and so on. And we'll only ask the validators to look at these references. So the key thing here is that the references are much smaller than the transactions, so now the overhead is smaller. But in parallel, what we'll do is we'll have something called verifiable distributed storage. So that you can think of this as a separate distributed service, and the full transactions will actually be dispersed in this distributed storage system. So the full transactions are being stored here, and the validators only look at the references of these transactions. But now during consensus, what the validators will do is, before they decide the ordering of the transactions, they'll go and run some verification with this distributed storage service to check that the actual transactions are being stored corresponding to the paper clips that they got. So once they verify, and like hopefully verification is efficient. So once they verify that the actual transactions are being stored, they can now run consensus on the paper clips and output an ordering on just the references or the paper clips.
I'm a little bit confused. What is the original purpose of these validators?
Sorry.
What's their tasks?
Oh, the main task is consensus, yeah? So like here, the validators, by consensus, I mean, for example, in the blockchain, what it means is like you have a bunch of transactions and you want to decide in what order do I put them in my blockchain. Yeah, so that's what I mean by consensus. Like they need to do consensus on what is the ordering of the blocks in the blockchain, like at a very high level. Yeah, so like when I mean you're ordering the transactions, these transactions will now go in the block on the blockchain. Yeah, good. Okay, so now once you have an ordering on the references of the transactions, now for the execution engine, it can go and actually retrieve the actual transactions from the distributed storage service corresponding to these paper clips and then go and execute the transactions. Any questions on the high level picture? Yeah.
So basically the paper clips is just to make the transactions shorter?
Smaller, yes, exactly. So you can think of those as like binding commitments, basically. That's what they look like in the actual construction. But yeah, like now basically, let's say if the paper clips were like 10% of the size of the transaction, then that means you can handle 10x more transactions. Yeah, so that's sort of like the high level idea. Good. So this is like a high level picture of we want to store the transactions separately and we want to do consensus only on the commitments or the public references to the transactions. Okay, so just going into the verifiable distributed storage part in a bit more detail. In one sentence, this is a distributed storage system where we are verifiably storing a large amount of data among a bunch of storage nodes. And the key goal here is efficiency. So we want that every single node in the system should only need to communicate and store a small part of the data. So we have storage nodes here. Actually, in the blockchain application, the storage nodes end up just being the validators. So you have a bunch of storage nodes. And then we have a disperser. This is usually the block builder in the blockchain setting. It gets a large amount of data, so it's like a big, you can think of it as like a block or a bunch of transactions. And then it disperses this data in these storage nodes. So each node will get a small amount of data, so it's like the small file. And it will also output the public reference, which will become the paperclip for this data. Then we want this verification thing because, as we saw in the last slide, for consensus, the validators will need to check that the actual transactions are being stored before doing consensus. So we have some verify protocol wherein you can talk to the storage nodes through some protocol to decide whether these nodes are actually storing the data or not.
So the disperser is powerful, and we only care about like the computation cost for validator.
The what cost?
Like we mainly want to minimize the cost of validator.
Yes. So like for example, naively, every single validator will look at all the transactions, which is like storing a lot of information. Here we're saying that like every validator will only need to store a small part of the transactions. Yeah, so like it's like a efficiency gain, I guess. Yeah, to scale consensus. Good. And the last protocol in the system is retrieval. So at any point in the future, if someone wants to actually get the actual transactions, they can again talk to the storage nodes through some protocol and get back the dispersed file. Okay, any questions on?
So there are two validators. Are they the same or different? Like
they are, so in the application they're actually the same, but for today's talk, let's think of them as different entities just for simplicity. But like actually in the consensus applications, the validators themselves are storing the chunks, and the validators are also verifying for consensus. So yeah, but like for other applications, it might actually be different parties. Yeah, so like that's why let's think of them as separate for now. Yeah, good. Okay, so just to give you some concrete examples, this thing called verifiable information dispersal or VID has been studied in the literature starting from CT 05. I think this is Kashan and Desaro. And this can be seen as a verifiable distributed storage system where the verification is non-interactive. So essentially what happens is once you disperse the data in some way, every node outputs a signature. So like node 1 outputs signature sigma 1 if it actually gets the chunk that it's supposed to get. And then to verify, you just look at signatures and you say that, oh, I accept if I see enough valid signatures.
Who keep the signature?
Oh, the nodes. So the storage nodes, once they get the chunk of the data, they will output a signature that certifies that I actually got the chunk that I was supposed to get and I'm storing it. Yeah, so like this is sort of how VID works at a very, very high level. And in practice, this is being used in EigenDA and espresso systems. Another example is something called data availability sampling. This has been formalized in 2023 by Hollanders and et al. And has also been implemented in practice in Ethereum and Celestia. And sort of like the key thing where it differs from VID is that verification is actually interactive. So the way a single verifier would check whether the data is being stored or not is it will literally go and sample random chunks of the data and then go query the storage nodes to give it that random chunk. And it accepts the data only if it sees that all of the chunks that it asked for are actually present. So this is sort of like a high-level picture of what data availability sampling means. It's a verifiable distributed storage system where verification is interactive via sampling, hence the name. Any questions on this? Okay, so today I'll be focusing a bit more on data availability sampling, but I do want to say that all of our techniques that we'll see today directly apply to VID as well, or like other examples of verifiable distributed storage. Okay, so the key motivation for this work was how do we repair lost chunks. So again, in this distributed storage system, what happens if, let's say, the last node loses the chunk that it stored, like maybe there was like a fire or like it lost its hard disk, for example. Or alternatively, maybe the disperser was malicious and it actually never gave that chunk to this node. Now the reason why this is bad is now if we think about verification, which is interactive, some of these nodes, if they query that last storage node, they'll actually not get any response from that because it lost its chunk. So all of the verifiers now have to talk to the remaining 3 nodes which actually have the data. Similarly for retrieval, now you have to talk to the remaining 3 nodes. But now the problem is it first creates some bottlenecks over the network because now you only have to talk to the subset of nodes which actually have the data. But secondly, if this keeps happening, so like imagine like today the last node lost its data, but now tomorrow let's say another node loses its data. And now you might just lose the data forever because you don't even have enough chunks of the data left. So because of this reason, we need to sort of think about repair more carefully and have an efficient way of repairing chunks which are lost in this distributed storage system. And sort of the efficiency problem I said, where like you can create bottlenecks by losing chunks, is something called griefing attacks. So repair is important to protect against griefing attacks and also to protect against like literally losing all of the data. So that was sort of like the key motivation for our work. And in our work, what we do is we make 3 contributions. The first is that we give new definitions for data availability sampling, where we start with the framework given by the 2023 paper, but we additionally formalize the notion of local repair, which is to repair chunks, and then also we formalize the notion of retrieval. And then we have a framework, a generic framework to construct data availability sampling schemes with local repair by design. And this framework relies on 2 building blocks. The first is a code with locality. I will define what this means in a bit. Plus something that we call an erasure code commitment with locality. Again, I will define this later on. And then we have a new construction of data availability sampling with repair, which uses multiplicity codes as the code with locality. Plus we have a new polynomial commitment scheme to act as the erasure code commitment with locality. And combining these 2 with our framework gives us a new efficient construction of data availability sampling with repair. So this commitment scheme actually might have other applications as well, but yeah, something we can see in the future, I guess. Okay, so I just want to show you quickly a comparison of our scheme with the construction of Ethereum, which is like the DAS deployed in their full fork. So in terms of node storage, this is saying how much data does every single node in the system have to store. So for Ethereum, every node has to store almost 8 kilobytes, whereas for our construction is just about 0.2 kilobytes. So like the total overhead of how much data every node has to store is lower by 35 times. Then we compare local repair, complexity, and we compare this across two metrics. So the first one is total bandwidth. So this means, let's say like I lost my chunk, I have to talk to other nodes to repair my chunk. How much bandwidth do I end up using over the network for that? For Ethereum, this is 128 kilobytes. For our scheme, this is much lower. This is just 21 kilobytes. So this is like you'll have to use 6 times lower network bandwidth to repair any single chunk. The second metric is something a bit particular to the Ethereum's network model. This is the number of subnets. So basically what subnets are like, yes. So what are subnets? They are sort of like, you can think of them as like a subset of the nodes in the network. And the way usually like the network, the distribution of chunks works in Ethereum is that every chunk of data is distributed across a different subnet of your network. And they call this the Gossip network model. So we don't have to go into details of that, but I just want to show that like if you count the number of subnets you need to join to be able to repair, we do have like 40% overhead in that, but it's still pretty reasonable for Ethereum's networks. But yeah, like I won't be focusing on the subnet aspect for today. The last two metrics are sampling bandwidth. So this says that like as a single verifier, how much do I have to sample the chunks to have some guarantee that data is being stored. And for Ethereum, this is 16 kilobytes. For us, this is just about 9 kilobytes. So we also improve in terms of sampling bandwidth. And I think the main sort of overhead for our scheme is this thing called dispersal work. So this is saying how much work does the disperser have to do to distribute the chunks. So it turns out we have like 40% extra overhead in this. We'll see why, like there's like some complications in the scheme, that's why we have this overhead. But we do believe that this is reasonable for Ethereum, given that the block builders have a lot of compute available in Ethereum. Yeah.
Is the data loss happens frequently?
Yeah, that's a good question. So that I think depends on your system, like how efficiently, like sort of how you're backing up the data. Yeah, I guess like we don't have numbers on how often this happens, but like given the large scale of Ethereum, like it's possible like at least like once a day some node loses its data, right? Just given like how many nodes there are, like something can go wrong at any point on those nodes. So yeah, I guess like the bigger your system is, the more you should care about repair, because like more things can go wrong. Yeah, good. Okay, so yeah, just like one small thing. So like actually for Ethereum, their scheme doesn't really guarantee retrieval in like some formal sense. So I just wanted to mention that. But like yeah, so even if you don't think about that, we already do have improvements in node storage, sampling bandwidth, and local repair bandwidth. Okay, so now let's look at our work in more detail. I will first start with the formal definitions. So I won't cover a lot given that we don't have a lot of time. So yeah, let's just get started. So this is sort of like the formal syntax of data availability sampling. This is an interactive protocol between a disperser D and the storage nodes, which I'll denote as N1 to Nn. We have a setup algorithm which outputs just the public parameters. So for example, this could be the CRS for your commitment scheme. Then we have disperse. This is the algorithm that the disperser will run with the input, the data which it wants to store, along with the number of nodes n. And this outputs a commitment com. So this is the public reference or the paperclip that we were seeing earlier, along with the chunks D1 to Dn. So node 1 in your system will store D1, node 2 will store D2, and so on. And then we have verify. So this is an interactive protocol. So these angle brackets tell you like who I'm interacting with. So the verifier can interact with the disperser or the nodes with the commitment as input. And then it outputs a bit B, denoting whether it accepts that the data was there, along with a transcript of everything it got from the network during sampling. And then we have something called extract. So what this does is, given the commitment and a bunch of transcripts, it actually tries to extract the actual data from these transcripts. And we'll see where this comes up in the definition at a high level. And then the two new algorithms we have in the framework. So like the first four algorithms were formalized by the prior work, and we sort of formally define the other two algorithms. The first one is retrieve, which takes as input the commitment, and this is an interactive protocol with the n nodes in the system. And then at the end of this protocol, you should get the data back, or you should get bought if you weren't successful. And lastly, we have local repair. This takes as input the commitment com, along with an index I. So you want to repair the chunk I. Again, you'll interact with a bunch of nodes, and then you'll get the chunk di, or you'll get bought if it didn't work. So this is just the syntax of data availability sampling. Any questions on this syntax?
So DI itself doesn't review the data.
Sorry, say that again?
Like only DI won't review the data.
Sorry, can you repeat that?
Sorry, like do DI like
Yes.
part of the data?
Yeah. So we'll see later on, like DI would be some subset of the data. So like, yeah, we'll see in a few minutes, like usually what we do is you encode the data with like some like linear code, like some code. And then you can, the DI will be like one part of the code. Yeah, so we will see that in a bit. Yeah.
So I just missed it. What is the second part of the output of verify?
So good. Okay, so what this, so this becomes important in definition, but basically, let's say if I am the verifier, I'll query nodes for random chunks. So then all the chunks that are received from the nodes is my transcript. So the second output is just the transcript I got. Yeah. Any other questions on the syntax? Okay. So in terms of properties, so I'll just be high level here. We have completeness, which says that if the disperser is honest and most of the nodes are honest, then verify should always accept and local repair should always work. Then we have two notions of soundness, which capture sort of like different guarantees of the system. The first one is something we call worst case soundness. So this is worst case in the sense that even if all nodes were corrupt, like literally everybody in the system was corrupt, even in that scenario, what we want to say is that if enough verifiers output 1, meaning a lot of verifiers were able to get a lot of chunks from the system, then we should be able to extract the data from their transcripts. So intuitively you can see like if the transcripts, like enough transcripts output 1, they must have enough chunks, so I should be able to extract. The second guarantee is for retrieval. So the optimistic case soundness says that if enough verifiers accept, along with that, if enough storage nodes are honest, meaning that the storage nodes are actually storing the data they're supposed to store, then we should be able to retrieve data in the future. Okay, so like sort of like the first one intuitively is saying that the data was dispersed over the network, and the second one is intuitively saying that I can actually retrieve in the future because enough nodes are actually storing the data that was dispersed. So it's like slightly different guarantees for the two. Yeah, I think the optimistic case soundness is like a bit new. Worst case soundness was defined by the prior work. Any questions on the high level definitions?
If the local repair succeed, do we guarantee the data is retrieved correctly, or we don't know?
Could you say that again? If
the local repair is successful,
right,
do we know that the output is like valid, or do we not know?
Oh, like the recovered chunk is valid or not? Yeah. So what we'll see in our constructions is that you can actually tell whether it was valid or not. Yeah. Good. Okay, so I will skip through the definition given the time constraint. Okay, so now let's move on to the DAS framework to generically build data availability sampling with repair from these two building blocks. So here's a more detailed picture for a framework for data availability sampling. So the prior work already had a framework where there is no local repair, but they show that you can build DAS from any erasure code plus an erasure code commitment. I will define this in a minute. And what we do is we say that, oh, if you replace the code with a locally correctable code, and you replace the commitment with a commitment which also has local correction, which I'll define in a bit, then you actually generically get DAS with local repair. So now let me start with all these building blocks one by one. So what is an erasure code? It's parameterized by k and n delta. We'll see what these mean in a minute. So an erasure code is basically two algorithms. You have encode, which takes as input a data. You can think of data as a vector of length k, and it outputs you an encoding, which is capital E. This is a vector of length n. And then the decode algorithm, which takes a subset of the symbols from your encoding and outputs the original data. So let me show you this pictorially. Think of the data as these 5 blocks, so k is 5. Then if you encode, you get a much longer string. So I have E1 to En, this is your encoding. And then what happens is, even if you lose some chunks of the data, let's say you lost symbol E2, you lost E5, you lost En, what decoding guarantees you is as long as you still have enough symbols, you should be able to run the decoding algorithm and get back the original data. So this is a standard erasure coding. So that's the first building block. Let's now see what the second building block is, which is erasure code commitment. So erasure code commitment is defined with respect to a coding scheme C. So an erasure code commitment for a code C can commit to the data in such a way that you can open this commitment to any position of the encoding. So formally we have the algorithm setup, which gives you some commitment key. We have the commit algorithm, which gives you the commitment. And then we have the open algorithm, where you take as input the data, the position I at which you want to open, and this outputs then opening proof by I. And then we have C verify, which takes us into the commitment key, the commitment, the position I, the symbol EI that you're claiming is the actual symbol at position I of your encoding, along with the proof pi I, and this gives you a bit 0 or 1 denoting whether the proof is valid or not. So at a high level, the key properties we want from an erasure code commitment are as follows. We need correctness, which means that if you honestly generate a proof, it should always verify. Then we have position binding. This is the standard notion for vector commitments, which says that no adversary can open the commitment to two different values at the same position. So this is again standard for vector commitments. But sort of the main thing that distinguishes this commitment scheme from a vector commitment is the extra property that is called code binding. So code binding says that you can't produce valid openings for a set of positions such that there is no code word that matches those positions. So essentially I'm saying that you can only commit to a valid code word. You can't just commit to arbitrary vectors in this commitment scheme. So as an example actually, if you think about KZG, which lets you commit to univariate polynomials, you can think of KZG as an erasure code commitment scheme for Reed-Solomon code, because you can only commit to polynomials which are valid code words. Any questions on this commitment scheme? Okay. So with these two building blocks, let's quickly see how we can build DAS by using these two. So again, imagine that the data you want to disperse is this vector with like these 5 blue blocks. I want to disperse this data. The first thing the disperser can do is just encode this data to get an encoding of encoding E, which is E1 to En. And then it will just, it will also commit to the data with the commitment scheme to get the public reference com. And then it also computes the opening proofs for every position of the code word. So it will get proof pi 1 for symbol E1, proof pi 2 for symbol E2, all the way till pi n for symbol En. And then the storage node 1 will store the symbol E1 of the encoding along with the proof pi 1. The second node will store E2 and pi 2 and all the way till n nodes. Oh, sorry. Okay, any questions on this? Okay, so now let's quickly see how we can run a verify algorithm in this setting. So as we already saw, like for verification, you just query random chunks. So what that means here is I'll be querying random positions of my encoding. So for example, let's say I'll query storage node 1 to give me E1 pi 1. I'll query storage node 3 to give me E3 pi 3, and also query storage node n to give it En pi n. And then I can verify each of these proofs with respect to the commitment com. So I'll output 1 only if all of them verify, meaning I did actually get the correct encoding symbols from all the nodes. And lastly, for extraction, basically this takes us into a bunch of transcripts. So let's imagine that this verifier got E1, E3, En. So we get these 3 symbols from this transcript. But now maybe we have another verifier, and that verifier in its transcripts gets a few other symbols, let's say E2, E5, En minus 1, and so on. So like basically if you have enough verifiers with all of them having transcripts which have a bunch of points that they got, you can basically get enough points, and then now you can run the decoding algorithm of your code to get back the original data. Good. So this is like a very high level picture of how you can build data availability sampling from a code and a commitment. Any questions? Okay. So just as an example, in Ethereum's PeerDAS, they use Reed-Solomon to encode the data, which is just encoding the data as a polynomial, univariate polynomial. And then they use KZG commitment scheme, which is a erasure code commitment for Reed-Solomon to commit to the data. Okay, but now the key question is, how do I repair lost chunks in this framework? So for example, imagine that the last node loses its data. So now we need an efficient way to repair the chunk EI that it lost along with the opening proof pi I that it lost. Now one thing I want to mention here is like there's always a very naive way that you can repair, which is you just collect all the other symbols and then run the decoding algorithm, and then that will give you the symbol EI and the proof pi I. So you can always do this, but the main point is to be more efficient than that. Because for literally every single chunk that we lost, we don't want to run repair again and again, retrieve again and again. So the goal is to do this more efficiently than doing the naive algorithm of retrieval. Okay, so this is where our new framework comes in, where the first building block is a locally correctable code. So what are locally correctable codes? These are special types of erasure codes where you can repair any position of the encoding by querying only a few other random positions. So pictorially, let's say this was an encoding, and let's say you lost the last symbol en. Then in a locally correctable code, let's say you only need to query 2 symbols, then potentially you can just query symbols 1 and 5, and then you'll be able to compute the symbol en from just e1 and e5. So what this means is like you won't have to now run the whole decoding to just repair en, you can just query nodes 1 and 5. Any questions on locally correct? Okay. So as an example, like the reason why Ethereum does not do well in terms of repair is because Reed-Solomon codes do not have locality. Like for Reed-Solomon, you'll actually have to query k positions where k is the length of your data. So that's like basically equivalent to just doing the full decoding. So just a little bit formally, we have algorithms encode and decode the same as before, but we also have a local correct algorithm which takes as input e hat. So this is a subset of the symbols from the encoding, position I, and this gives you the repaired position ei. So that's the first building block, locally correctable codes. But the main thing is from the commitment side, how do we repair the opening proofs? And that's where a new notion of erasure code commitments with local correction comes in. So what we say is like we need a commitment scheme which is an erasure code commitment, but it should also support local correction. So in one sentence, we should be able to repair the opening proof of any position by querying the opening proofs of only a few other positions. So as an example, let's say this was your encoding and you could repair en from e1 and e5. What we would like is the same thing for proofs. So if you lose pi n, ideally we should be able to repair the proof from the opening proofs of pi 1 and pi 5. So basically the same positions you need for repairing the code, hopefully you should be able to repair the opening proof with the same the proofs for the same positions. Any questions on this? Okay, so just formally defining the syntax, we have setup, commit, open and C verify the same as before, but we now also have C local correct, which takes as input a bunch of symbols ej along with proof pi j for a subset of positions s, and then it gives you the opening proof pi I for the ith location that you lost. In terms of properties, we have correctness, position binding and code binding, same as before, but the extra property is local correction. So I guess in one sentence this says that if the local correction for the code works by just querying a few symbols, then the local correction for your commitment should also work given the opening proofs of the same symbols. Okay. Any questions on this? Okay. Okay, so we've now defined the 2 building blocks for data availability sampling with local repair, a locally correctable code, and an erasure code commitment with local correction. So now let's see how we can change the framework from before to get local repair by design. So this is the framework we saw before. We have an encoding and a commitment, but now we'll just change them to the locally correctable versions. So I'll now encode the data with a locally correctable code LC. For the commitment, I'll use a locally correctable commitment to commit instead of like a normal one. And again, the opening proofs will be with respect to the locally correctable commitment. So now for the repair protocol, let's say if the last node loses its data, then if, for example, I can just query nodes 1 and 5, I can get symbols E1, E5, and I can repair the symbol En. And again, I can repair the proof pi n from positions proofs pi 1 and pi 5. So this gives you an efficient way to do repair, both for the code and the commitment. Any questions on this?
What is the usual ratio between R and N? Like how large is N in practice?
Oh, N can be actually pretty large, like it will be like thousands or like let's say tens of thousands, for example.
How about R?
R depends on the code you use. So like for example, the code that we will use, I think R ends up being square root, proportional to square root of N. So that's like one example, but like actually that's like an interesting question because there's a lot of codes in theory, like in that people have studied, which have local correction, which have different like trade-offs of R, like how large R is. And then that's actually like a good question, like what's the right code to use such that it has small enough R, but it's also efficient in other ways. Yes, I'll briefly talk about this in a few slides. So this is the formal theorem we prove for the security of the resulting DAS scheme. We basically say that if your commitment scheme satisfies all these properties like position binding, code binding, and actually a few other properties, then you achieve soundness for your resulting DAS scheme. Oh yeah, one more thing I want to mention is actually, like especially for data variability sampling, there are some subtleties in exactly what network you use for dispersal, and that actually turns out to be important in proving that retrieval does actually work. So we also do some formalization of the gossip network in our paper. Okay, so yeah, this is just like a summary slide. The previous framework was how the full DAS of Ethereum is instantiated. But with our scheme now, with our new framework, we can use multiplicity codes plus a new commitment scheme to get our new data variability sampling scheme with repair. Okay, so now coming to actually your question, these are the two building blocks, and I just want to briefly talk about what's the right way to instantiate both these building blocks to get good DAS schemes. So for example, if you think about node storage as one of the metrics, in our framework, each node has to store one symbol of the encoding of the locally correctable code, but it also has to store one opening proof for the commitment scheme. So what this means is that for node storage to be small, your opening proofs should be small. Next, for disperser work, if you look at our framework, the disperser has to run the encoding algorithm of the code, and it also has to compute the opening proofs for all positions of your code. So this gives you another constraint. This is saying that the encoding algorithm for your code should be efficient, but also you should have an efficient way of computing the opening proofs for all positions. So if you can keep going, for repair complexity, we need efficient local correction, so we need R to be small. And again, we need the local correction for the opening proofs to also be reasonably efficient. And lastly, what we show in the paper is that the sampling bandwidth, meaning how much you have to sample for a single verifier, actually depends on the distance of your code, like the minimum distance. So this means that your code should also have good minimum distance. And this is sort of like the key interesting part in building data variability sampling or like verifiable distributed storage in general. We want to be able to co-design locally correctable codes with all these properties, plus corresponding erasure code commitment schemes with all these properties to get efficient verifiable distributed storage. So now let's move on to the last part, which is our new construction with multiplicity codes plus a new commitment scheme. So let me start with a quick refresher on multiplicity codes. So multiplicity codes are a special type of erasure codes which have good local correction. These were introduced by Koparty et al. In 2014. And you can think of them as a generalization of Reed-Solomon codes in the following way. So we interpret the data as a multivariate polynomial of some degree. So in particular, let's focus on bivariate for today. So we can think of the data as some polynomial f of x comma y. And now the encoding of this data will contain the following things. It will contain the evaluation of f at all points x comma y in some set S. So this is similar to Reed-Solomon where you store the evaluations of the polynomial at a bunch of points. But there are some extra things that we will store. We will actually also store the evaluations of derivatives of this polynomial. So we have f prime x, this is the first derivative with respect to x, and f prime y, which is the first derivative with respect to y. So we'll also store the evaluations of these derivative polynomials at all points x comma y. So just pictorially, the code looks like this. So the first symbol E1 of your code will have the evaluation of f prime x, and f prime y at the point 1, 1. This is what the first node will store. Then similarly, you will have E2, which is the evaluation of all these three polynomials at 1, 2, and you can keep going like this. So basically, for a bivariate polynomial, the encoding is this matrix where you have evaluations at all points I, j for I, j in Q. Okay, so I want to highlight two key properties of multiplicity codes which make them a good choice for building DAS. The first is that they actually have good distance, good minimum distance, and intuitively the reason why is that you're storing extra information. So like every node, instead of just storing the evaluation of f, it's also storing the derivatives f prime x and f prime y. It's basically giving you more information about what the polynomial is. So because of that, even if you lose more symbols, you can still actually decode. So what this means is like our sampling bandwidth for the resulting DAS scheme is actually smaller. And the second key property is that it has good local correction, and this turns out to be important for local repair. So to show you why local correction is easy here, let's imagine that you lose EQ, the symbol on the first row on the right. Then let's focus on the first row of this matrix. What we have is we have the evaluation of f at 1, 1, 1, 2, 1, 3, all the way to 1, q. So I can actually think of these evaluations as evaluations of a univariate polynomial f of 1, y. And now this univariate polynomial also has degree d, where d is the degree of a polynomial. And now we know that if you have d plus 1 points on any polynomial of degree d, you actually have enough information about the polynomial. So what this means is that in this row, if I collect d plus 1 symbols, any d plus 1 symbols, I can actually use those to recover f of 1, q. Any questions on this? Okay, and turns out you can do the same thing for the derivatives because they also have degree d. So, like R, basically R, the parameter for this scheme is the degree d in this setting. And now the nice thing is that you can actually do this along any line. So you can think about the diagonal, and again the points on the diagonal are actually a univariate polynomial of degree d. So you can do repair on the diagonal, you can also do it on the column. So like you can basically draw any line through the point, and as long as you get d plus 1 points on that line, you can actually do repair. One last thing I want to mention before we move to the commitment is that for this multiplicity code, we actually give an efficient encoding algorithm, which is order k log square k, where k is the length of your data. And the key property here is that our algorithm lets you do systematic encoding, which means that the code word actually contains the data in the clear. So this becomes important for efficient retrieval. But for this, I think I'll refer to the paper for more details. Okay, so any questions on multiplicity codes before I move on? Okay, so moving on to the last part, which is a new commitment scheme that allows you to commit to multiplicity codes. So our new commitment scheme is the first polynomial commitment scheme with the following properties. It allows you to do opening proofs for the evaluation of the multivariate polynomial as well as the derivatives. And recall that this is important because if I'm committing to the encoding the data with multiplicity codes where I'm storing derivatives, I need a way to efficiently prove that the derivatives are actually correct. So that's why we need opening proofs for the polynomial along with its derivatives. So the opening proofs for our scheme, if you let's say have a bivariate polynomial with only f prime x and f prime y, the proof size is just 3 group elements to verify any single symbol of your encoding, and the verification just takes 4 parents. The two other properties are we have an efficient batch opening algorithm. So recall this was important for the disperser to be efficient so that I can compute all opening proofs efficiently. And the third key property of a commitment scheme is that we can do efficiently local correction of opening proofs, and this was important for local repair. So I guess at a very, very high level for the commitment scheme, we'll actually generalize PST, which was by Elaine. And the batch opening is a generalization of Korodowick-Feist technique to multivariates. Okay, so for the commitment scheme, let me start with a refresher on PST, and then we'll see how we can open proofs for derivatives. So here we are working in groups of prime order P. We have a bilinear pairing E, so I'll consider symmetric groups for now. And I'll be using additive notation, so like square brackets x denotes g to the x. So the setup has a CRS, which is powers of tau. So because we're in a bivariate setting, we have tau 1 and tau 2 for x and y. And then the commitment key will contain tau 1 to the I, tau 2 to the j for all values of I comma j until the degree. So this is like all monomials of a degree d polynomial. To commit to a polynomial, you just output f of tau 1 comma tau 2, the group element corresponding to this. And to open, so this equation will be important, so I want to go through this. To open the polynomial f at a point a comma b, you compute quotient polynomials q1 and q2 such that f of x comma y minus f of a comma b is equal to q1 times x minus a plus q2 times y minus b. So this is sort of the equation of how you can prove the evaluation of f at a point a comma b. And then the proof of the point a comma b becomes the evaluation of q1 at tau 1 tau 2 and the evaluation of q2 at tau 2. Any questions on this equation? Okay, so this is like all standard PST. And to verify at a high level, we can check this equation in pairings in the exponent. I'll skip through this. This is just checking the same thing with the exponent. Okay, so now the main thing is how can I prove the evaluation of the derivative f prime x at some point a comma b. So again, this is the equation we've already seen. F of xy minus f of ab is q1 times x minus a plus q2 times y minus b. So now what we'll do is we'll just take derivatives on both sides and see what happens. So on the left side, I'm taking x derivative here. So on the left side, I'll get f prime x of x comma y, and f of a comma b is constant, so its derivative is 0. On the right hand side, we can apply chain rule. So I'll get q1 of x comma y times 1 because the derivative of x minus a is 1 plus x minus a times the derivative of q1, and the remaining term actually they don't have an x, so the derivative will just be 0. So this is the equation you get if you just take the derivative on both sides. But now, if we actually put x equals a and y equals b, which is the point that we care about, what we actually get is that the derivative f prime x evaluated at the point a comma b is exactly equal to q1, the quotient q1 evaluated at the same point a comma b. So like the x minus a term just goes away. So this is one of the key observation we'll use to be able to do an opening proof for the derivative. So in one line, to prove the evaluation of f prime x, the derivative, at the point a comma b, we can just open the quotient polynomial q1 at the same point. And by opening, I mean doing the PST opening proof, which means you can compute quotient polynomials q1a, q1b for the quotient polynomial q1, which is like again the same equation as PST, just applied to q1. Any questions on this? Okay, so it turns out we can do the same thing for f prime y. So if you just take the y derivative instead of the x derivative, you get this equation, but the main thing is if you put x equals a, y equals b, you get that the evaluation of f prime y at the point a comma b is equal to the evaluation of q2, the second quotient at the point b. So now again, to prove the evaluation of f prime y at the point a comma b, we can just open the quotient q2 at the same point. So again, you just like open the, compute the quotient polynomial q2b for this polynomial. So combining it all together, the opening proof at a point a comma b would be the following things. We'll have q1 and q2, which are the opening proof for f, same as PST. But now we'll have extra terms to prove the derivative. We'll have q1a, q1b, this is the opening proof for q1. And we'll have q2b, this is the opening proof for q2. And then to verify, we'll just check the 3 opening proofs in the exponent. So I'll just check that these 3 qualities hold via pairings, the usual way through from PST. So this is like a high level picture of what an opening proof might look like if you extend PST for derivatives. But this is still like not super efficient because here the proof size is 5 group elements, and verification actually if you count all these equations, it turns out you'll need to do 8 pairings, which is a lot. So what we actually do is we observe that these 3 equations, we can actually combine them together in like one big equation, and then turns out you'll only need 3 group elements in your proof, and you'll only need to do 4 pairings instead of 8. So like this optimization really helps us a lot in getting like better efficiency in smaller proofs. Any questions on this high level picture?
Do we get the same security level then?
Yes, yeah, we do. Actually, so that's what we formally prove. Like we actually prove security based on the same assumption as PST. So like we're getting the same level of security. Yeah, good question. Okay, so yeah, this is the formal statement. So we prove position binding for our modified PST, and turns out we can prove it based on the same assumption, which is decisional S strong BDH. This is the same as PST. So yeah, just to summarize, in our work we have new definitions where the main thing is introducing local repair, and we saw a DAS framework for generically getting DAS with local repair from codes with locality plus erasure code commitments with locality, and then we saw a new construction which uses multiplicity codes plus a new polynomial commitment scheme. Oh yeah, so just before I conclude, I want to mention the 2 other features of the commitment scheme. Again, we have efficient patch opening for proofs at all positions, and this is important for dispersal work, and we have local correction for opening proofs. There's also like one more thing where we talk about optimizing the network part, like the peer-to-peer gossip network things, using some type of batching on top. You can find details in the paper. Yeah, I guess to conclude, hopefully I've convinced you that local repair and data availability sampling is an important problem. And what we saw today was a new data availability sampling construction, which achieves efficient repair from multiplicity codes and a new commitment scheme. I guess in terms of open questions, the first big one is using other locally correctable codes to build DAS with repair. So there are other codes which also have like good local correction, like expander codes or folded Reed-Solomon codes. There's also something called Tama codes and so on. But then the idea would be to also have a commitment scheme that lets you commit and do opening proofs for that code. So that's sort of like the crypto part of this question. And lastly, something for game theory folks is to design mechanisms to actually incentivize honest nodes to store their data. So for our sort of framework, we assume that honest nodes always store the data, but like it would be nice if you could also get the same guarantee if the honest nodes were rational, in that like they might not store the data if they don't have incentives to do so. So yeah, I think with that I'll conclude. Thank you.
What is the benefit of using other locally correctable code?
Yeah, that's a good question. So I think there's like a trade-off in like the distance and the parameter R, like for the repair parameter. So yeah, actually I'm forgetting what does expander do. But so yeah, for example, the third actually parameter, right? So like if you recall, when I showed the comparison, I said that like with multiplicity codes there is an overhead. Like the dispersal work, actually there was a 40% extra overhead because you have to compute the derivatives and everything to encode. So like it's possible that with some of these codes, maybe the encoding aspect, like the encoding algorithm is maybe more efficient. So the dispersal work might be better. So there's like a few sort of like, there's like a design space here, right? In terms of local repair, your distance, and then the efficiency of your code. So there's like a few things you can play around with. Yeah.
I also have a question about like how this is used in practice. Like
Okay.
in practice, do we update, like do we have more data chunks over real time, or do we stick with this constant number of data chunks? Do we increase the number of data chunks over time?
Oh, chunks. Oh, that's a good question. Good. Okay. So I think at least in Ethereum setting, I think the number of chunks is constant. But actually, I'm glad you mentioned it, because with local repair, it might be possible to, let's say there's like, if a new node arrives, then actually with local repair, it will be faster to like get them a new chunk. Because like I'll only need to contact our other nodes and I can compute a new evaluation point, right? Whereas with Reed-Solomon, you'll actually have to contact a lot of nodes to actually reconstruct the polynomial first and then give them a new point. Yeah, so like local repair also helps you with like updatable committees. Wow, that's a great point. I should probably add that in the slides. Yeah, you also had a question.
Oh yeah, I probably missed this, but how do you locally repair the commitment? Is it also the same way you repair the adversary code?
Oh yeah. Actually, I didn't have time to like go through it. But sort of what happens is like in multiplicity codes, I can just talk about KZG. So like if you imagine KZG opening proofs, the opening proofs are just like the quotient polynomial evaluations in the exponent. Is it a one? Oh yeah, I guess.
Oh yeah.
So I'll just tell you how it works for KCG, and then like for our commitment, it's like a generalization of that. So the opening proof by I is in square brackets, it's the quotient I, right? Evaluated at.
I think you might want to use it in front of it.
Okay. Okay, never mind. Yeah, so sort of the
Like this?
yes.
I see.
Oh, okay. Oh yeah, that's actually really good. Okay, so for KCG, the ith proof is the evaluation of the ith quotient at tau. So actually the nice observation is that these QIs, you can think of them as, so these QIs are actually also related. Yeah, actually it's a okay, I don't remember the equation now. But turns out like if you have the quotient evaluation of a bunch of points, you can actually also compute the quotient evaluation of a new point. Yeah, so that, okay, we'll have to remember the equations a bit more. But like, yeah, let me open up my paper actually.
So then, the reconstruction is in the exponents.
Yeah. So the intuition is like you're sort of doing some interpolation in the exponent.
Yeah.
And like because it's just linear, I can do that.
Yeah.
So like KZT again, like there's some relation in the quotients. So for our commitment scheme, we again derive like similar relations in the quotients for our multivariate commitment scheme, and then we observe that you can even interpolate those multivariate quotients in the exponent. Yeah. So like it's a bunch of like complicated equations. Yeah, sorry, I've. Okay, maybe if there's other questions, I can maybe take them first.
I remember you mentioned like at the beginning of the talk something about like the Ethereum subnets as well.
Oh, Gaussian subnets, yeah.
What was that exactly?
Okay, so this subnets is like the network model or like the network implementation in Ethereum. It's like this gossip sub. So sort of what happens is you have different subnets, meaning like so like let's say I had like 10 chunks to disperse. What happens is like if I am let's say node I, I'll subscribe to the subnet for that chunk. So like there's like let's say 10 subnets each for every chunk. So then like there'll be a bunch of nodes subscribed to every subnet, and then what happens is that the disperser just needs to give the ith chunk to some party in the ith subnet, and then basically everybody gossips it to each other within that subnet. So it's like that's how they have implemented the network to like, for example, they use this even for dispersing transactions. Like they use this gossip sub where like you have subnets and like everyone gossips transactions to each other. So there basically what you want is like me as a node, I want to like let's say for local repair, I'll have to join a few let's say I wanted the chunk of node 1 to repair, I'll have to join the subnet for node 1 so that the people in that subnet can gossip the chunk to me. Yeah, so then like that's why it would be nice to have like less subnets in the system. So like for example for local repair we have some extra subnets that you have to join, but like that's still reasonable for the network. Yeah.
So it seems that there are many metrics. Like, do you know which metric is like more important or some metric are not important? Like, for example, is dispersal work important? Because I think it's just one time thing.
That's a good point. So dispersal work so depends on your application as well. But I do agree that in consensus, usually the disperser is the block builder. And actually in Ethereum, they have like very big machines because they're trying to do like MEV on top and like other things. So like the block builder is actually like, it's okay to have more disperser work actually. That's why we were also okay with the trade-off. But I think node storage is something, node storage and repair are something that it would be good to have smaller node storage because that makes your system more scalable, right? Because like you can store more like you can store chunks for more data if your chunks are smaller. Yeah.
So basically, communication cost, like the storage cost, is the main bottleneck in this.
At least in the Ethereum setting for consensus, yes. But like if you have like other applications in mind, then maybe like it depends on the application. Yeah. Okay.
Okay, if we have no more questions, let's thank the speaker again.